All right, so we're going to talk about matrix factorizations, section 2.5, and in fact, we're going to talk about something called the LU factorization. So this matrix A here, this is a matrix A, and this matrix A, it turns out, has this particular LU factorization. It has an LU factorization such as that. Now, how did we get that? How do we get the LU factorization, and what does that mean? Well, all right. Well, let me give you a moment to copy it. Let me give you a moment to copy that. L times U. Notice the first matrix L below the diagonal. Well, what do you see above the diagonal on the first matrix L? What do you see? What do you see? What are the only numbers you see above the diagonal? Let me say it again here. So matrix L, matrix A can be written as L times U. Above the diagonal of ones, you see zeros. That's right. So why are they calling this matrix L? That's right, Mikhail, that's right. And somebody else said, okay, yes. So L is lower unit triangular. It's a lower unit triangular matrix because the zero entries are all above the diagonal. The density, the non-zero terms, the dense part of the matrix, we call it, are below the ones. Now look at the matrix U. Look at the matrix U. There are the zeros above or below the diagonal in the matrix U. They're below. What is the matrix U? What form is that matrix U? What form is that? I mean, we can call it, we can think of it as upper because the zeros are all below the diagonals. So the non-zero entries or the dense part of the matrix is in the upper part of the matrix. But what form is the matrix U in? What form is it in? Good, it's in echelon form. That's right. Good, Belen, good, Mikhail. So we can take a matrix A and factor it into a product of a lower unit triangular matrix L and an echelon matrix U. And it turns out that this is very, very helpful for solving a system of equations. What we want to do is we actually want to use that LU factorization. Okay, hold on. We want to use the LU factorization to solve the matrix equation A times the vector x equals the vector b, where b is equal to negative, has components negative 7, 5, and 2. Negative 7, 5, and 2. So, you know, you've learned now multiple ways to solve a system of equations. You do row operations on it, get the system reduced down to reduced echelon form and solve. You've learned that you can, if it's a square matrix, say, you can, and it's invertible, then the solution vector x will equal A inverse times the vector v. And now you're seeing yet another way to solve. You're going to see another way to solve this system. So let me take you through this. Okay, don't worry about how we got the LU factorization right now. Don't worry about that. But let's use it to solve that system of equations. So here's what we do. Here's what we do. Take a look. Okay, so I replace the matrix A with L times U. And because matrix multiplication is associative, instead of writing L times U times the vector x, I can write L times the vector U times x. And I'm going to call the vector U times x my vector y. So there's an intermediate vector. There's an intermediate vector. Well, there's a vector y. We want to solve for that vector y. So you see what we're doing now is we're treating this matrix equation as the matrix equation L times y equals the vector b, where y is equal to this vector u times x. But the matrix equation L times y equals the vector b would be represented as the augmented matrix, as this augmented matrix. And what we're going to do is we're going to solve this augmented matrix for this vector y. Now the vector y is not the vector we're interested in, it's the vector x. We want to solve for the vector x. But we're going to solve for y first. So what I do is we have that lower unit triangular matrix here to the left of the dash, and then the vector b over here. So this is vector b, and this is the lower unit triangular matrix. So let's think about this now. We want to get pivots. We want to get pivots where the -1 is, right? Let me just blow this up a little bit. We want to get pivots. We want to get zeros, sorry, where the -1 is and where the 2 is. So what we're going to do then is we're going to take 1 times row 1, add that result to row 2, replace row 2 with that result. And we're going to take -2 times row 1, add that result to row 3, and replace row 3 with that result. Just a couple of row operations, no big deal. And then we have a 5 here, so we have a 5 here, right? So we'll use the one above as a pivot. We have our pivots here. We'll use the one above as a pivot. So we're going to take 5 times row 2, add it to row 3, put the result in row 3. And look at what we have here. Is this augmented matrix in reduced echelon form? It is, absolutely. This is in reduced echelon form. What is y1 equal to? Good. That's right, Bella. -7. What's y2 equal to? Good. -2. And y3 equals 6. Okay. So we've very easily solved for that intermediate vector y. And it was easy to do because because the augmented matrix involved a lower unit triangular matrix, and so we had all these zeros up here above the diagonal, and so it made the system very easy to solve. And by the way, it would make it easy for a computer to solve too. Well, now that we know the vector y, remember what we had. How was y defined? Well, u times the vector x was equal to y. Now that we know what y is, we can solve this equation for the vector x. So that's what we do. Now we're going to solve the augmented matrix that you see here. Okay, so augmented matrix. This is the matrix U. This is the echelon form of the matrix A. And then here's the vector Y. And again, you have zeros in half of the matrix, which makes life, you're cutting down on half your work, basically. So you're basically, you're dividing the work up into two simple systems that are easy to solve. Now we have to work upward we do is we take the third row, multiply it by -1, and replace that result in the third row. Well, okay, no problem. We want to have zeros where the -1 and the -2 are now, so we'll use the 1 as a pivot. We'll multiply row 3, add it to the second row, and replace the second row with that result. And we'll take row 3 and multiply it by 2, add it to row 1, replace row 1 with that result. Please let me know if there are any questions. Okay. Where that -2 is, I'd like to make it a pivot of a 1. So I'm going to take the second row, multiply by -½ and replace the second row with that result. That gets me second row of 0, 1, 0, 4. Now we have a pivot of 1, and we'll use it to get a 0 where the -7 is. Okay. So now what we're going to do is use this one as a pivot to produce a 0 where that -7 is. And we'll do that on the next page. So what we did was, let me just go back for a minute. We obviously took 7 times row 2 and added that to row 1 and replaced row 1 with the result. So 7 times row 2 plus row 1, replace row 1 with that result. Easy to do, and now we get a nice augmented matrix, and we can solve for the vector x. So this is a really lovely method because instead of, I mean, you have two simple systems of equations to solve. Okay, you're breaking up the row operations. You're breaking up the problems so that you have two simple systems of equations to solve. The question is then, how do we take a matrix A and write it as L times U? Okay, how do we take a matrix A and get this LU factorization? All right, well, let me bring up the algorithm in the book. One moment. Hold on. Are there any questions so far? All right, let me go to the book here. So here's the algorithm for an LU factorization. And the algorithm, you can prove it using the proof if is in the previous page. And if we have a chance, we can look at it tonight. If not, we can maybe look at it on Monday. But it involves elementary matrices. The proof involves using elementary matrices. And here's what you're going to do. Here's what you need to do. You reduce the A to echelon form, to an echelon form matrix U by row replacement operations if possible. And I want to mention that the row replacement operations, right, you have 3 kinds of row operations. One is to multiply a row by a number and add that new row to another row and replace the other row with the resulting sum. Okay, that is, let me just see here. Let me go back to section 1.1, or maybe it's, yeah, page 6, elementary row operations. That's called replacement. You replace one row by the sum of itself and a multiple of another row. Okay, and for the LU factorization type examples that you're going to see in the book in section 2.5 and in the homework, you're going to be doing row replacement operations. Okay, but you're not going to be doing any interchanges. It's strictly going to be row replacement operations. Okay, so you're going to have to, the technique that you're being shown here is I'm gonna show you how to do an LU factorization. MATLAB will not give you the same answers as the MyMathLab homework ones. Okay, you have to work it out by hand because MATLAB involves, when they do an LU factorization, they involve what's called partial pivoting, and we'll talk about that next week. So the MATLAB algorithm to do an LU factorization involves partial pivoting. It's going to involve row interchanges. For section 2.5, the homework, they do not want you to do, well, row interchanges are not going to be needed. So again, MATLAB, when it does an LU factorization, it involves row interchanges to get the LU factorization. But for your homework problems, there's no row interchanges needed. They're not going to do any row interchanges, so you've got to work it out pretty much by hand to get the answers. Okay, so what we want to do is we want to do a sequence of row replacement operations to reduce the matrix A into echelon form U, and then we're going to do the same sequence of row operations to reduce this lower unit triangular matrix to I. So to the identity. So let's say here, for an example, okay, for an example, and I'm going to go to a handout that I have, but I want to write the example down here. Okay, so example is let the matrix A equal, I'm going to give you a 4 by 4 matrix here. First row is 3, -7, -2, and 2. Second row is -3, second row is -3, 5, 1, and 0. Third row is 6, -4, 0, and -5. And the fourth row is going to be -9, 5, -5, and 12. This is a 9, -9, I should say. Now what we want to do is we're going to write this matrix A. You know, we want to find L and U such that the matrix A equals L times U. And incidentally, the matrix A is a 4 by 4. That equals L times U. The matrix L is going to be also a square matrix, 4 by 4. And so the matrix U, well, matrix U would be a 4 by 4. I got to be a little careful how I say this. If we're going to reduce this matrix A here to echelon form, then of course it's a 4 by 4. But that means then that the lower unit triangular matrix cell would have to be a 4 by 4 because a 4 by 4 times a 4 by 4 would give you a 4 by 4 matrix. Okay. Are there any questions so far? Okay, then let me get to the right page here. Okay, so solution. Now there's part of this you can ignore. The top part, one moment here, clear. You can ignore the top part, okay? You can ignore the top part here. Forget about this part. We're just finding the LU factorization of A. So here's what we do. On the left, on the left side, you notice there's a big old dark bold line here, right? There's a big old, hold on here. So there's a line here. Oh, don't do that. Come on, don't do that. Big bold line. Okay. Now, what we do is we say, okay, let's start with the matrix A, and let's reduce it. Let's try to get it in echelon form. Well, we know that what we want to do is we want to get zeros where the -3, the 6, and the -9 are. And I'm going to stick with row replacement operations. So normally what I would do is the 3 here, which is the pivot, right? That's the pivot. Normally what I might do is I might multiply through the first row by a third so that the pivot would be 1. But we're not going to do that. We're just going to do row replacement operations. So we want to get zeros where the -3, 6, and -9 are. So these are the row operations. I'm going to multiply the first row by 1, add to row 2, and that result will go in row 2. And then to get a 0 where the 6 is here, I'll take the row 1, multiply by -2, add to the third row, result goes in the third row. And finally, where the -9 is, to get a 0, I'll take 3 times row 1, add it to row 4, result goes in row 4. Okay. And this gave us the 3 zeros here. Now, what I did at the same time is this. The first column, so I'm remember what I'm trying to do here is construct L times U. So at the same time I'm constructing my matrix U, my echelon form matrix U, I'm also going to construct my matrix L. So you notice how I circled here the first column of the matrix A. Well, I put that first column over here. And what we did was we did these row operations, okay, and now this is the second column, the numbers below the -7, and I put those numbers over here, okay. Now what we have to do, again, it's an algorithm. Don't right now, just take it on faith. This is what we're doing. Now what I have to do is I want to produce a 0 where the 10 is and a 0 where the negative 16 is, using the negative 2 as a pivot. So I'm going to take 5 times row 2, add it to row 3, put the result in row 3. Okay, that's so that I can get a 0 where the 10 is. And then I'm going to take negative 8 times row 2, add it to row 4, and put the result in row 4. That's so I can get a 0 where the negative 16 is. Okay. Notice there are no row interchanges, and I'm not scaling any row by a number. It's simply row replacement operations. Okay, well now we have in the third column a negative 1, 3 right here. We're going to use the negative 1 as a pivot, right? Negative 1 as a pivot, and I move the negative 1, 3 over here. So what we do now is, since we want a 0 where the negative 3 is, I'm going to take the third row, multiply it by negative 3, add it to the fourth row, and the result goes in row 4. Then I'm going to have a negative 1 down here at the bottom, in the bottom right. So I put a negative 1 here. Now the matrix U is upper triangular, but let's just call it echelon, okay? Because you can do LU factorization on non-square matrices also. So I just want to be careful about the terminology. I mean, I'm not saying upper triangular is wrong, but I like to think of U as echelon form. But it is upper triangular, right? It is. I mean, that's true also. No row interchanges were used. Okay. So you can't do this using MATLAB, because MATLAB uses row interchanges because it uses partial pivoting. And we're going to discuss that next week, what that means. All right. Okay, now what I do is this matrix L on the bottom right is a lower unit triangular matrix. That means that we need to have ones along the diagonal. Have to have ones along the diagonal. So what we do is we say, okay, if I were to take the first column and divide through by 3, I do that so I can get a 1 where the 3 is. Now, technically speaking, that's not a legitimate row operation. You can't divide through a column by a number. You can divide through a row by a number, but you can't take a column and divide it by a number. But this is an algorithm, so it's just a procedure that works. The second column has negative 2, 10, and negative 16 in it. Well, where the negative 2 is, I want a 1 there. So I'm going to divide by negative 2, second column. Similarly, I'll divide by negative 1 on the third column, because third column, I want to have a negative 1, a positive 1, I should say, where the negative 1 is. So I'll divide by negative 1. And then I'll divide by negative 1 on the fourth row also. And this is going to give me my lower unit triangular matrix. And if you were to take matrix L, Okay, take matrix L and multiply it by matrix U, you would get back matrix A. You would get back matrix A. And you can check that in MATLAB. Okay. Now, the very interesting thing I want to make you aware of here. Very interesting thing. In the lower unit triangular matrix here, what was the first row operation did? We took, let me just maybe put it in blue here. Make it a little bigger. Yeah, we took row 1 and added it to row 2 and placed the result in row 2. What if we, in the lower unit triangular matrix, what if we took row 1 and added it to row 2 and replaced the second row by that sum? What will we have in the second row? What is row 1 plus row 2? What's the row that results when we take row 1 plus row 2? Okay, that's right, Mikhail. 0, 1, 0, 0. That's the second row of an identity matrix. That's the second row of the identity matrix. The I sub 4, identity matrix, 4 rows, 4 columns. Okay, let's look at the next row operation that we did in producing, to get matrix A, to get it into echelon form. We took -2 times row 1 and added it to row 3 and put the result in row 3. So if I were to take -2, if I were to take -2 times row 1 and added that to row 3, okay, well, I want to be a little careful here. That's not going to get you, I mean, I guess what I'm trying to say is, if you were to do, yeah, it would get you 0, -5, 1, 0. That's right. And then if you did 5 times, well, here's what I'm trying to say. I want to be careful how whoops, hold on, I lost my whole thing. Hold on, let me get it back. Hold on. Here's what I want to say. These row operations that we did, these 6 row operations that we did, if we did those same 6 row operations to the lower unit triangular matrix L, those 6 same row operations would reduce that matrix L to the identity matrix. That's what they're trying to emphasize here. And this is why this works. Okay, and we can actually go over the proof on Monday. Let's look at another example here. I want to look at another example. Okay, let's find the LU factorization for this matrix. Let me give you a moment to copy it down. Now notice this matrix is not a square matrix, right? What are the dimensions on matrix A? What's the size of matrix A? It's a 4 by 5. 4 by 5 matrix. That's right, Mikhail. That's right, Cameron. I'm pleased to see we have some more participation from other students here too. That's good. That's good. You know, nobody's ever going to make fun of you if you say a wrong answer here, you know. Well, we're not actually solving a system of equations here. We're just trying to get this matrix A we're trying to find the LU factorization of this matrix A. Yeah. Okay. So what we're going to do is we're going to while we're reducing the matrix A to echelon form U, we're going to be constructing at the same time our lower unit triangular matrix. All right, may I go to the next page? Are we, so far we're good? Okay, excellent, Cameron. All right, well, let's go to the next page. So here's the matrix A. There it is. And what I want to do here, hold on, let me just, one moment. One moment. Right, so what do we want to produce here? Where the -4, the 2, and the -6 are. What numbers do we want to be there? Zeros, that's right. So we're going to use the 2 as a pivot. Okay, and let's see what we did here. Let's see what we did. Well, looks like we did 2 times row 1, added it to row 2, put the result in row 2. Usually I put my commands, my row operations on the right, but I'll just write them on the left because I have space. And then we did what? Negative row 1 plus row 3, put the result in row 3. And then to remove this 6 here, this -6, using the 2, we'll have to do what? What's the last row operation we have to do to get a 0 here? What do we have to multiply row 1 by? Right. Good, Mikhail. 3 times row 1 plus row 4. Put the result in row 4. Okay, and this is your result. Now, incidentally, right away, I took that first column and I put it here. And now, the second matrix, I'm going to take the 3, -9, 12, put that here. Okay. Sometimes we separate it with columns. We just write those rows as columns, or those columns as columns over here. Now what do we have to do? Well, we have to do some more row operations. We want to have zeros where the -9 and the 12 are. So we're going to take what? We're going to do 3 times row 2 plus row 3. Put the result in row 3. And then we're going to do -4 times row 2 plus row 3. Put the result in row 4, I'm sorry. Right, row 4. Okay. Now we're going to take that 10, -10, and that's going to form our next little column here. Quite fascinating, really. Does it help my writing these little row operations here? Is that how many of you is that helping a little bit? Is that? Oh, okay, wonderful, wonderful. Thank you, Cameron. Thank you, Marcella. Okay, so now okay, now I focus. Hold on here. Okay, so now where that -10 is, I want a 0. So I'm simply going to take row 3, add it to row 4, place the result in row 4. And now we get down to here, and I circle the 6, and that's what goes up here. Is this matrix here in echelon form? It is, absolutely. We can't do anything more. It's in echelon form. And notice again, the row operations were limited to adding a multiple of one row to another row. That's how these problems are designed in section 2.5 in your homework as well. So if you try to use MATLAB to do the LU factorization, it will not be what the MyMathLab wants. Okay, so you just have to remember that for section 2.5, and of course for your exam next week too, right? So now we do the same thing. We want a lower unit triangular matrix, right? We want lower unit triangular matrix. So the algorithm, well, Mikhail, yeah, we have 5 exams in the final here. Yeah, somebody told me the other day, well, Dr. Duty, do you give quizzes? You know, because some professors will give quizzes in addition to exams. But I tend to like, you know, exams are where the big points are. But by giving 5 exams, you get tested a little more frequently. So it's kind of like, well, you're not quizzed every week, but you know, you don't go too long without an exam. All right, Cameron likes the smaller exams. Okay, wonderful, wonderful, as opposed to like just 3 exams Nice to hear that, Cameron. Thank you for that input. Thank you for that input. So, okay, first column, we'll divide through, we want the 2 to be a 1, we'll divide by 2. Wonderful, Mikhail, thank you. I'm glad you like this system too. The 3 here, we want a 1, so we'll divide by 3 on that column. The third column, where the 10 is, we want a 1, so we'll divide by 10. And then the 6, we want a 1 there, so we'll divide by 6. And that gets us that square matrix. The lower unit triangular matrix is always a square matrix. Okay, it's always a square matrix. And the same row operations that reduce the matrix A to echelon form would reduce this matrix L to an identity. And note that the matrix A in this problem, it's a 4 by 5 matrix, right? The matrix U is naturally a 4 by 5 matrix. So of course, the only matrix L that's going to work is a 4 by 4 matrix. So the algorithm for finding LU factorization works for non-square matrices as well. Now I'll make a comment here before we. I want to make one more comment here before we close. Just give me a moment here. Are there any questions on this example? Okay, and by the way, you can check that L times U equals A. You know, of course, you would want to do that for an exam, right? And you should do it for your homework. Why not, you know? Okay, so I want to go back to the ebook here. One moment, everybody. One moment. Let me just go back to the ebook. Yeah. So they have an interesting numerical note here. Okay. So again, when you're dealing with very, very large systems, you have to worry about how many flops are needed to solve a system of equations. A flop is a mathematical operation. And they just talk about how the LU factorization takes about 2n cubed over 3 flops. Okay, but finding A inverse requires 2n cubed flops. So, you know, 2n cubed is more flops than 2/3 n cubed. So even though the LU factorization, and I'm really discussing this first comment here, even though the LU factorization, hold on here, let me just, I mean, when you solve a system of equations using an LU factorization, you have to get the LU factorization of the matrix A, and then you have the two systems of equations to solve. Finding the LU factorization takes 2/3 times n cubed, whereas if you were to solve a system of equations using an inverse, you would need 2n cubed flops. So that's 3 times as many flops to get the inverse. But then they mention in the second comment that solving then these two little systems of equations requires 2n squared flops. So if you add up what's needed in the LU factorization to solve a system of equations, there are less flops overall involved in solving a system of equations. And that's why LU factorization, they mention it here, LU factorization is a faster algorithm than using like, x equals a inverse times b to solve a system of equations. Okay, so these, how many find those numerical notes kind of interesting at the end of the sections? I think they're pretty cool myself. How many think this is kind of cool? Yeah, Bellin likes it, and I know we have some computer science majors here. All right, are there any questions before we stop the recording here? Okay, I'll stop the recording.